we are back to our hardware design again, and when there's the pop-up window saying bitstream generation completed, it means our process of generating the bitstream completed. You could cancel, because at the moment we don't need to open anything from here, so we click cancel. We'll go back to that window when we initiate some debug function in our hardware system, but at this moment we only try to do the introduction. After we do so, after we finished designing the hardware system, finish generating the bitstream for the hardware design, we need to export those into a file, and that file will be the foundation for the software development in SDK. Now we go to File, we go to Export, and we choose Export Hardware File. Of course, we need to include the bitstream that we just generated and export to the local project. Yes. So as here you can even see the information for this hardware file. The export hardware will be used at the foundation as the platform for the software development tools, and the software development tools will be the SDK that we will launch after the export hardware file is finished. We can go to maybe messages here, or the TLC console. You can see many messages, and based on those messages we will know that okay, the exporting hardware file has been finished. So now we can launch our SDK, and when we run the SDK, we choose everything as default and we press OK. And then we wait for SDK to start. Now it starts the SDK. And we need to be patient and waiting because the launching has not been finished. Importing hardware specification. This is the hardware file that we just export from Vivado. Okay, at this moment, let's check our board. So at this moment, my board is not connected to my computer. However, when I'm inside the software development step, so earlier we do the hardware development step, the hardware block design step in Vivado, and after we finish the hardware we need to go to the software. And when we need to go to the software, we need to really connect our board to the computer. Now let's connect our board. So as you can see, this is the USB board. To connect my board to the computer, and when I connect the board to the computer, there's a LED on here to indicate okay, my board is connected to my computer now. So that's a good sign. And now here's our software. So this is the system platform specification based on the wrapper that we generate in the Vivado. So based on that wrapper, it has many information, but in order to apply this information to our board, to our Zynq chip area here, we need to click on the program FPGA, and when we press on the program FPGA, you could see that the hardware platform is the wrapper that we generated, and also the bitstream is the generated bitstream based on our hardware design that we did earlier. So now we will specify those bitstream and the files in the VRAM memory to our Zynq chip in order to implement the software, implement the brain into the body. Now we implement the body into the chip. So we press program. and we wait for the configuration. So the first thing when you want to do the software development, first you need to press on Program FPGA, because clicking on Program FPGA can help us to program our FPGA. And based on that, there will be many parameters got extracted and got the header file. So based on that header file, we can manipulating many things inside our chip. And now we will create a software project. You go to File, go to New, and we choose Application Project. We can say Introduction, Application, Software. For our software development step will be the name for the project name of the application. We choose OS Platform Standalone. Standalone means our application will be the bare metal application. Usually the application will be controlled by the operating system, and that operating system will operate in our Zynq chip, but now we will eliminate the operating system layer and we implement our application directly on the chip. The language that we use is C, and we need to use the board support package. We click next and we choose Hello World. It will be like the very beginning template for our software development. So we click Finish. And we wait. And we wait. And on the Project Explorer, you could pay attention. There are 2 folders created. And the building process has not been finished yet. As you can see here, the building workspace is only 14% and the log is still running. So we need to wait until everything has been finished properly. Otherwise, we might encounter some problem, maybe. Okay. It's finished for creating the application project. Now we go to our introduction application. We go to the folder source and we open the Hello World source file. And here they will init the platform. The init platform comes from, if you want to know where it comes from, you can move your mouse to the command and you press Control and click on the command. It will guide you to the file where it contains that one. So this is the file where it contains our init platform. Now we'll go back to the Hello World. So this is what we are expected to do when we want to init the platform in our Zynq chip. And this print Hello World means it will print a message on our console. And in order to print some message on our console, we need to establish the communication between my computer, between this software with the board outside here. So we go to SDK terminal. So this terminal will be where can see some messages printing from this software or the message sent back from the Zynq chip. In order to have the message, we need to have the communication established between my computer and the board. In order to do so, there will be the green plus symbol here to add the serial port. We click Add, and then we choose the board where we connect our board to. If you don't know which COM that my board is connected to, we can go to the device manager and we go to ports, COMs. So my USB serial port is COM9. I will choose COM9. And the baud rate, as you can see, there is some information about the baud rate for my computer. So the baud rate is 115200 configured by the PSP, which is we choose from the beginning. That's why we need to choose the 115200, because our Zynq chip will be configured based on this PSP with the baud rate 115200. My baud rate for the computer should be on the same rate with the chip in order to communicate with it. So we click OK. Okay, now we already set up our communication between the software and the chip. And before we do anything further, we need to press program FPGA. This is a very important step. We must do this step before doing anything further. And we press program FPGA. Program FPGA means program our Zynq chip. And then we wait it to be done. And the program FPGA on our Zynq chip is done because the programmable logic area, just like the FPGA area of our Zynq chip. So now that part is done. We can try to build this code and launch it to see what will happen. And usually now we can see we are at the console. However, in order to see any message sent from the Zynq chip or something, we need to be at the SDK terminal. So we need to choose the tab SDK terminal. After we press program FPGA, we need to build the code into the executable file. And after the building has been done, now we will launch our application to our Zynq chip. Launch on hardware. And the launching process now has been done. When the launching has been done, we will be automatically jump to the console. In order to see any message, again we need to choose SDK terminal. And here, hello world. And you can see the hello world. This is the hello world message sent from our Zynq to our computer, and that message is shown on the SDK terminal. So again, when we launch the application, when we launch our executable file, we launch this file into our chip, and when the Zynq chip browses through the whole code, when it executes this line, the Zynq chip will send a message hello world. The Zynq chip will send a message hello world to our computer, and our computer after that our computer will send the message hello world to our software in the SDK terminal. So this is the message that we received from our Zynq chip according to the code that it has been programmed, has been launched on it. And now we will go to our task. The code that I will copy for the blinking task, for those blinking LEDs, will be provided in the comment section as I mentioned from the beginning. So please just go to the comment section and you can copy the code that I demonstrate in this part. But now I will have a little bit of pause to find the code and I will be back. Okay, now I already copied the code for the blinking task and I will start to go through the code a little bit. Then we will try to launch that code to see whether it works properly. But before explaining anything further, let's try to launch this code to see whether it works. Then after that we can start to explain through the code. Now I just need to build my code. I only need to press program FPGA once when I first start my SDK. But after I already press program FPGA, I don't need to press it every time that I launch a new application on the chip. I just need to rebuild my application and then I will launch the new executable file on the chip. and we should expect to have some blinking on the LEDs. Oh, I have a problem here, so I just have to delete it. Okay, after I modify my code, I press Ctrl S to save it, or you can go to File to save your modified code, and then I rebuild my code and I will relaunch it. The launching is in progress. Okay, now the launching has been finished. We need to go back to SDK terminal and we see lots of messages, and we can see that our LEDs are on, but it's not blinking because I haven't set it to be blinking. However, I can turn on my LEDs and that's good. So now we can go through the code and then we can try to modify this code to make the LEDs blink. We can clean this terminal. So the next time when we start a new program, the terminal will be clean and we can easily track what has been happening. So let's go to the hardware schematic. When we do our software development in SDK, we must be aware of what is the role that we are on, which perspective that we are writing the code. In order to easily understand, we should imagine that we were the Zynq processing system part here in the Zynq chip. We are only the Zynq processing system part. We are here. We are this part. And the only part that we can communicate, because we are the Zynq processing system part in the Zynq chip, and the part that we can communicate is only the Xi-GPIO. For us, we only see the Xi-GPIO in the Zynq chip. We cannot see those 4 LEDs. As a result, whenever we communicate means you read or write to the Xi-GPIO. We are the Zynq processing system. If we read or write to the Xi-GPIO in the Zynq programming logic area, it will be equivalent that we are writing or reading from the LEDs, from those LEDs on the board, even though we only see the Xi-GPIO in the chip. We only see the Xi-GPIO in the chip, but we already, when we design the hardware, we already established the connection between the Xi-GPIO to the LEDs. However, when we write the software in SDK, we were as if the Zynq processing system part. So the only thing that we can communicate in our code is the Xi-GPIO. We can only communicate which are on the same chip, which are inside the chip. So that's why, again, when we write this code, we should imagine that we are the Zynq processing system, and the only thing that we can see is the Xi-GPIO 0. The Xi-GPIO 0 here. Let me explain it. So you can see this is the Xi-GPIO 0. This is the only thing that we can see. So if we want to write or read to the LED, we need to read or write to the Xi-GPIO 0 to the appropriate interface where the Xi-GPIO connected to the LED. So in the code or in the Zynq chip, The XRTVL 0 represents our LED. Now we need to initiate our XRTVL in the code. Even though we already designed the XRTVL in the hardware diagram, but in the software we need to appropriately initialize it in order to use it. So here is the variable with the type X GPIO, and this is the variable. This is the variable representing our XRTVL. But at this moment, it's totally an empty variable. We need to initialize it. So, in order to initialize it, here I wrote it down. In order to initialize it, we need to have two steps. The first step is that first we need to look up for the predefined configuration of our GPIO, because we launched our SDK based on the hardware file imported from Vivado, where we already have every configuration information of our GPIO 0. We need to look it up so we can initialize our variable in the software according to the predefined configuration of our GPIO in the hardware. So at this step, we just look up for the information of our GPIO, and after we already have all of those information, we will initialize our GPIO 0 instance to use in this code. So here you can see we reuse the looked up information to initialize our GPIO 0. And after the two steps, now as the Zynq processing system, we can communicate to the XRTVL already, because we already initialized that XRTVL, so now we can communicate to the XRTVL with this variable. What variable? Yeah, this variable. So remember, after declaring the variable, an empty variable to represent our XRTVL, we need to initialize, we need to put the content in that empty variable GPIO to make it like a real XRTVL 0 in order for us to communicate with it. And after we initialize our XRTVL 0, we initialize it already, right? Now we need to configure this XRTVL as if we were doing with this XRTVL, as if we were dealing with it in the hardware. So in the hardware, what were we doing? We create this instance XRTVL, and after we create this instance XRTVL, we connect our XRTVL, or we configure our XRTVL at the port 1 connect to the LED. In the software, we will do similarly. In the software, we initialize our variable XRTVL. So the next step should be, we should configure in the software at which port or at which interface of our instance XRTVL connect to the LED. So this is the step that we configure our XRTVL 0. We configure our instant XRTVL at the channel, the LED channel. The LED channel, if you want to see what is the value of this LED channel, you can just put your mouse here and you will see number 1. So LED channel means value 1. In other words, this is the interface 1, corresponding to our hardware design, where we have the LED connected to the interface 1 of our XRTVL. So in the software, we also have to configure our XRTVL at the channel number 1, which is the LED. as the output system, because we're gonna use our LED to indicate the value that we send to the LED. That's everything about how we're gonna use the Zybro. As a summary, I will again say it one more time. In order to communicate with the LED, because we are the Zynq processing system, the only thing that we can see is the Zybro. Because the Zybro is inside the Zynq chip, and we as the Zynq processing system also inside the Zynq chip. As a result, we cannot see the LEDs directly. We can only see the Zybro, and because we can only see the Zybro, we can only communicate with it. However, in the hardware design, we already designed our Zybro to connect to the LEDs on the Pynq board. So whatever we communicate to the Zybro, it is equivalent to communicate to the LEDs outside the chip. To do so in the software perspective, there will be also similar steps. In the software, we need first to initialize our Zybro 0. We create a block Zybro 0, and then after we got the Zybro 0 instance, we will configure at which channel of that Zybro in the software is connected to the LED. So there are two steps are very similar to the hardware design of the Zybro, right? Very similar. And after we have our GPIO instance initialized and configured, we can communicate to it in order to manipulate our LEDs. And I hope that is gonna be a good summary. Now we can try to modify the code in order to make the LEDs on the board blink. One means we will have a loop runs for forever. It will run until somehow we turn off our board, otherwise our board or our chip will keep running in this loop. That's the meaning of while one. And the meaning of this line means we will negate the value of the LED and then assign to our LED variable the new value. Negate operator means, for example, if the LED has the value 0, then the negate of the LED will have the value of 1. Another example, if the LED has the value of 1 and then the negate of the LED will have the 0, 0. So that's the meaning of the negate operator. And then we save it and we will build our new code, and then we launch our new code on the chip to make it execute the new code. So we should expect to see some LED blinking. And now the LEDs are blinking. So we finished our task.